Linear Algebra, a lecture on the mathematical concept of vector spaces. A vector space is a set V of vectors equipped with two algebraic operations, vector addition and scalar multiplication. The first, vector addition, says that for any two vectors in V, so given vectors v1 and v2 in V, their sum is also in V. The second algebraic operation, scalar multiplication, says that if we have a vector v1 in the set capital V, and a scalar alpha, then alpha v1 is also in V. Now intuitively, what is going on here? To give you an intuitive understanding of what's going on behind the symbols, let's make an analogy. A vector can be thought of as an instruction. To relate it to normal life, it might be an instruction to take one step forward, say. Or take two steps to the right. Now suppose, armed with these two instructions, you find yourself on the third floor of a block of flats. You can quite easily imagine that with just these two instructions, you could walk everywhere on that third floor, as long as you were allowed to do two things. Firstly, do a combination of two instructions, e.g. walk forward one step and then take two steps to the right. The combined effect is this. And secondly, do the same instruction multiple times, e.g. take one step forward 3 times. The combined result is this. Or even take a negative multiple times, e.g. take -1 steps forward. So you take a step backwards. With just these two instructions, we can now walk everywhere on the third floor. This is a useful analogy for the mathematical concept of vector spaces. Thus, for a given set of vectors or instructions, combining two instructions is like vector addition. And doing the same vector or instruction multiple times is like scalar multiplication. In this example, the crucial thing for you to understand is that vector space is the whole of the third floor, i.e. it's everywhere you can go with our two instructions and our rules for combining them. Note, and this is an important point, our vector space does not include the other floors in the block of flats. Why? Because we didn't have an instruction which allowed us to go to other floors, e.g. allow us to take the lift. Okay, one final caveat. Our analogy isn't perfect, and there are some distinctions that we need to make. Firstly, a vector space doesn't have to be just 2 dimensions. It could be 1, 2, 3, or infinitely many. Secondly, the scalar in scalar multiplication isn't necessarily a real number. You could have a complex vector space, for example, where the scalar is complex instead. However, the most important difference to understand is that in a vector space, no matter how many times you do vector addition or scalar multiplication, you always remain inside the vector space. In fact, this is a defining property of a vector space. For example, if you repeat an instruction in our analogy, e.g. walking forward one step again and again, eventually you'd reach the edge of the building, a wall on your floor. In a vector space, this doesn't happen. Instead, you can continue combining vectors infinitely many times, i.e. the floor extends forever. This is a hugely important distinction, and in fact, we shall see later that a key test for a vector space is whether the floor eventually stops or whether it extends onwards. So in other words, the way we test later on, we'll find whether something is a vector space is to see, okay, let's keep combining vectors. Are we going to reach a wall, or is it going to keep allowing us to combine and always remain inside the vector space? In the next lectures, we shall go into more detail about the properties and rules of vector spaces, as well as introduce some specific examples of vector spaces. The key takeaway from this lecture about vector spaces is to realize that a vector space is all the space that can be reached through scalar multiplication and vector addition of a given set of vectors. Or to use our analogy we used before, the vector space is like the third floor of the flat block.